All right, let's dive right in. Today, we are heading to the absolute edge of what's possible in computing. We're talking about a world that is bizarre, that's completely counterintuitive, and that honestly might just change everything. We're talking about quantum computers. And our story really begins with a simple rule that has defined our entire digital lives.
For most of our lives, we've been riding this incredible wave of progress called Moore's Law. It's a pretty simple observation, really. The number of transistors you can cram onto a chip doubles roughly every 2 years. And this relentless, exponential growth, it's the reason the phone in your pocket today is literally millions of times more powerful than the computers that took us to the moon. It's been an amazing ride.
But there's a problem. This incredible progress is about to hit a fundamental physical wall. We're getting so small so fast that we're approaching the point where transistors are going to be the size of just a few atoms, and you just can't get any smaller than that. So if we want computing to keep getting better, we can't just keep doing the same thing. We need a completely new idea.
And it turns out, the seed for that new idea was planted way, way back in 1959. The legendary physicist Richard Feynman gave this amazing talk where he just imagined. He imagined what we could build if we operated on the scale of individual atoms. He realized that down at that tiny subatomic level, the rules of physics themselves change, opening up, as he put it, completely new opportunities for design.
And this brings us to the hero of our story today, quantum computing. Now, it's super important to get this straight. This is not just a faster version of the computer on your desk. No, it's a fundamentally different way to compute, built on the strange and frankly wonderful laws of the quantum world.
So, what are these different rules? Well, think about it like this. In our everyday world, the classical world, if you throw a baseball, you can calculate its exact path. It's predictable. But down in the quantum world of atoms and electrons, things get fuzzy. It's probabilistic. You don't know exactly where something is, only the chance of where it might be. It's a world built on uncertainty and pure potential.
Now, if this is already starting to sound a little bit weird, please don't worry. You're in very good company. The same guy, Feynman, famously said, "Nobody understands quantum mechanics." The point isn't to get it in a common sense way. The point is to accept the nature is, well, kind of absurd at this level, and then learn how to use its rules.
So the difference starts with the most fundamental building block. A classical computer, like the one you're using right now, uses bits. They're just simple switches that are either off or on, a 0 or a 1. A quantum computer, though, uses a qubit. And a qubit, well, a qubit is special. It can be a 0, it can be a 1, or, and this is the mind-bending part, it can be a combination of both at the exact same time. And that one difference unlocks almost unimaginable power. This ability to be in multiple states at once is one of two quantum superpowers we really need to wrap our heads around. The first one is called superposition. And the most famous way to think about this is a classic thought experiment you've probably heard of, Schrödinger's cat. Imagine a cat in a box. In that box, a vial of poison might be released based on a completely random quantum event. The bizarre reality of quantum mechanics says that until you open that box and look, the cat exists in a superposition. It is both alive and dead at the same time. So that both at once state, that is superposition. And because a single qubit can hold both a 0 and a 1, a string of qubits can hold and process every single possible combination of those numbers all at the same time. This lets a quantum computer attack a problem from all angles at once. It's a kind of massively parallel computation on a scale that's just hard to even imagine. Okay, the second quantum superpower is even stranger, if you can believe it. It's called entanglement. This is what happens when two or more qubits become linked in this deep, mysterious way where their fates are intertwined.
If you measure one of them, you instantly know the state of the other one, even if it's on the other side of the galaxy. Albert Einstein himself was so baffled by this idea, he famously called it spooky action at a distance. It's a connection that just seems to defy all of our everyday logic, but it's a fundamental feature of the quantum world that we're now actually learning how to harness. So, okay, we've got these incredible and kind of spooky properties, superposition and entanglement. But how do you actually control them to do a calculation? You do it using these incredibly precise tools called quantum gates. The easiest way to think about quantum gates is that they're the building blocks of a quantum circuit, kind of like logic gates are for a classical computer. They perform very specific, tiny operations on the qubits, tweaking their state in a really precise and, this is important, reversible way.
So for example, there's this one really important quantum gate, and it has one profound job: to take a simple qubit that's in a definite state, a 0 or a 1, and pop it into that powerful state of superposition, where it's both at once. This is the tool that really unlocks that quantum parallelism. It switches a qubit from a state of certainty to a state of pure possibility. And this is where it gets really amazing. When we start combining these simple gates, we can create these truly powerful quantum effects. This circuit you're seeing here, that's basically the recipe for creating that spooky state of entanglement we were just talking about. By applying a couple of simple gates to two qubits, you can link their fates together perfectly. We are literally building circuits to control the quantum world. I know, this all seems incredibly abstract, but this ability to engineer superposition and entanglement is exactly what unlocks a future that could redefine what's even possible. So, really, why does all of this matter? Because the potential applications are absolutely staggering. We're talking about discovering new drugs by simulating molecules with perfect accuracy, creating financial models that are practically unbreakable, optimizing global supply chains, building climate models that are far, far more precise. These are the kinds of huge, complex problems that are simply impossible for even the biggest supercomputers we have today. Now, you hear a lot about how quantum computers, using things like Shor's algorithm, could one day break all of our modern encryption, and that's a huge deal. But what's so fascinating is that the same quantum principles offer a way to make encryption unbreakable. It's a real double-edged sword. This diagram here shows a concept called quantum key distribution. By sending information on single particles of light, Alice and Bob can create a secret key, knowing for a fact that if anyone tries to spy on it, the very act of observing will disturb the system and reveal the spy instantly. Pretty cool, right? Okay, so before we get too carried away, it's really important to know where we are on this whole journey. And the truth is, we are right at the very beginning. We're in what's called the innovation trigger phase. The promise is enormous and the excitement is absolutely real. But those truly world-changing applications, they're still a ways down the road. Right now, we are in what experts call the NISQ era. That stands for Noisy Intermediate Scale Quantum. Intermediate scale means the machines are still pretty small. A noisy means they're really delicate and prone to errors from the tiniest disturbance, like a change in temperature or a stray vibration. The grand challenge for scientists and engineers right now is finding useful problems that these imperfect but uniquely powerful machines can solve better than any regular computer. So the quantum revolution, it isn't some distant science fiction dream. It's happening. It's happening right now. It's noisy, it's incredibly difficult, but it is underway. And as we get closer and closer to building machines that can truly solve the unsolvable, we're left with this profound and exciting question. What monumental challenges will we, as a species, choose to take on first? Thanks for watching.